Welcoming everyone to the third session of the day. In this session, we're going to talk about reserves. May I take the opportunity to welcome the esteemed panelists for this discussion uh, on the topic NP industry. He has wide-ranging experience as well-site geologist, development geology, GNG interpretation, and reserve estimation. We welcome you, sir. I would also like to welcome Mr. Harshvardhan and Mr. Shashank Singh, who will be presenting on the topic Ravva Field Technology Implementation to Realize True Field Potential and Way Forward. Harshavardhan is a principal geophysicist working in the offshore assets of Cairn Oil and Gas Vedanta Limited. He leads the reservoir characterization endeavors for the offshore development team and is responsible for the FDP planning and execution. We welcome you, sir. I would also like to welcome Mr. Shashank Singh, who is a senior reservoir engineer working in the offshore assets of Cairn Oil and Gas Vedanta Limited. He leads the reservoir engineering function for the offshore team and is responsible for implementing the reservoir management plan. We welcome you, sir. I would also like to welcome Mr. Dustin Fife, who would be presenting on hydrocarbon reserves and resource estimation in deepwater fields. Dustin Fife is a head of Subsurface RIL. He graduated with a degree in petroleum engineering, highest honors, in 1983 from the New Mexico Institute of Mining and Technology in 1983. We welcome you, sir. I would also like to welcome Mr. Pankaj, who would be presenting on the evaluation, classification, reporting, and auditing T12 field. Pankaj has 14 years of experience in reservoir simulation and operational reservoir management with key focus on major chemical EOR application. He is currently working as the head of reservoir engineering with Antelopus Energy. We welcome you, sir. I would also like to take the opportunity of welcoming the moderator of the session, Mr. Amitabh Pandey. Mr. Amitabh Pandey is the head reserves and resources in Cairn Oil and Gas Vedanta Limited. He has 15 years of experience in Cairn in EOR design and implementation and reservoir management of prolific Mangala, Bhagyam, Aishwarya fields. We welcome you, sir, and may I now request you to commence the session and take over the slides.
Thank you. Thank you, Chandrima. So welcome everyone to the last session before the lunch break. And resources, their capex, identify opportunities, rank them, and make forward plans. And it is also very, very important for the lenders because it allows them to know the value of a project and the projected cash flows, and it helps them to make decision to finance for financing or not. And for government entities, again, it is very important because it helps them to understand the value of their national assets and also helps them to ensure whether the assets are being properly managed by the operators, the oil companies, or not. And again, coming to the customers, especially for gas buyers, it is very, very important so that they are assured of long-term commitments or long-term commitment of supply. And for all these matters, it becomes very important that the operators and oil companies, they follow robust technical processes to estimate resources and reserves, and also get it independently validated through third-party certified reserves auditors periodically, so that it gives comfort to all the stakeholders. I think with this brief introduction, I'll start the session. And as we know, we have 4 presentations. And for each presentation, around 15-minute time is allotted. So I'll request everyone to manage the time. And at around 10 minutes into the presentation, I'll give a small burst so that we can plan the overall presentation properly. So I would first like to invite Mr. N.C. Das from ONGC to present his talk, to give his talk on discovered resources and adoption of PRMS in ONGC. Welcome, Mr. Das.
No, sir, it's not. Yeah, it's open. Yeah, it's visible now. Yeah.
Okay, thank you, Mr. Pandey. I think at the outset, I must thank DGH and the organizer providing this platform for exchange of ideas with all the ENP operators in India, along with some experts from overseas experts. Then, good thing is that this PRMS, I think almost all the professional bodies, they are at one single platform from the ENP industry. I think earlier, SP and WP classification system, which were widely followed before PRMS came into being, it was only geological confidence. Range of confidence was the prime criteria. But in the world of, you can say, commercial world, it was not working. And aptly, this PRMS was introduced in 2007. Then it came 2011 guidelines were issued. So effectively, you can say 2011, we had PRMS guideline was effectively introduced in 2011. So ONGC, I think we started our reserve estimation in 1965. We had first estimation. We followed Russian system. Then it continued up to 1994 when we introduced that SP WPC classification system. 1987 classification was introduced in 1994. That continued up to 2018-19. So 2014-19, this PRMS was rolled out in ONGC. So what is PRMS? PRMS combines a range of geological uncertainty, the charts of commerciality of petroleum resource classification. So before my presentation, a lot has been said. It will be very simple. I think it covers discovered resources in ONGC. So discovered resource I will be covering and fundamentals actually. Many of the operators who are new to this, I think it will be very clarity and simple way I will explain. So what is petroleum in place? All quantities of petroleum that are estimated to exist originally naturally occurring accumulation. Most important is naturally occurring accumulation prior to production. They can be discovered and they can be undiscovered. Let us see what is discovered and what is undiscovered. So discovered PIP, they are from known accumulation, estimated for known accumulation. Undiscovered, they are yet to be discovered. So let us go, let us maybe one step ahead. So discovered resources, the application of all the technology available today. Some, I think major portion is still unrecoverable and certain portion is recoverable. With this recovery component, we cannot, what are the components of recoverable? By application of, we can have the three components: production, commercial, sub-commercial. I am showing this, how the concept of PRMS came, that basic behind the PRMS philosophy. So when in a recoverable resources, we have not applied any project, commercial, it is called sub-commercial. When you apply a project, it is a commercial, and production is what has been produced so far. So reserve is excluding the production from the commercial part. Similarly, undiscovered, they will have, when discovered, they will have unrecoverable component, they will have also recoverable component. And this recoverable component will have also, this left hand diagram, you can say this is graphical representation of PRMS. So this vertical axis, y axis, this is degree of commerciality stage. As you go up, on the top it is reserve, which one are commercial is contingent resources, and the bottom is prospective resources which is yet to be discovered. Then what is then horizontal? This is geological uncertainty or certainty, you can say. As you go from left to right, this is, you can say, proved. In case of reserve, you can say proved, possible, or probable. So with incremental, you can say that is confidence decreases towards the right. Similarly, and when you say P1, in scenario case, this P1 is called 1P, and P1, P2 case is 2P, and P1, P2, P3 is 3P, or it is equivalent to low based high estimates. On probability term, they are P90, P50, and P10. Similarly, equivalent is C1 in contingent resources, C2 and C3, or they are called in scenario case 1C, 2C, and 3C. And prospective resources, they are called 1U, 2U, 3U. I do not know why PRMS they could have introduced U1, U2, U3. It is not there. So let's right hand side. Again, these classes, reserve, contingent resources, and prospective resources. So PRMS guideline says these are must. Everybody should apply this. Subclasses also are there based on the what is the project status. They can be subdivided into subclasses also, or maturity classes, subclasses. As per guideline, they are not compulsory, but I think companies for internal management, for they are a must actually. They may not be reported, but internal management and every company should follow this principle. So I will discuss in detail when you go. So as you go vertically, play lead prospect. So I will be covering the discovered resources, that's how commercial part. So it's contingent resources and reserves. So when I say C3, C1, C2, C3, the C3 is technically equivalent to possible of a reserve, but they are not sub-commercialized. When I talk of C2, they are technically equivalent to probable reserve, they are not commercialized. Similarly, C1 also equivalent to proved, but they are not proved actually. They are still awarded to be commercialized. Maybe they are just pending to be commercialized. So discovered petroleum resource classes and subclasses. So how we adopted in ONGC. Left hand side, that is PRMS 2018. How we adopted in ONGC, I think slight change, almost philosophy is intact. We wanted to make it the boundary between contingent resource and reserve to be foolproof. It should not be left to it's subject to interpretations. So we said it is not justified, it should be justified, approved for development. Why just approved for development? Approved we mean financial approval. Unless otherwise there is financial or management, it cannot be called reserves. That is why we had slight change to this PRMS guideline. So that should be no ambiguity in future. Next is under implementation and under production. So with these changes, we have adopted PRMS in 2019. So again, I will simplify reserves. How we call reserves? Their quantities commercial recoverable by application level project. There should be discovered first. They should be recoverable. They should be commercial, and they should be remaining. The production amount which has been produced, it is not called reserve, so that should be excluded. So remaining in the subsurface, then it is reserve. So contingent resources is similar, they are discovered, recoverable, but they are sub-commercial. Why sub-commercial? Because of contingencies. What are contingencies? They can be market, they can be technology, they can be technical, maturity evaluation process is not complete, they can be environmental, political, social, and regulatory. Any one of the contingencies there, they will be called contingent resources. So I typically have added that line I have drawn. Below that is unrecoverable. Discovered PI is recoverable is above. That what is recovered? Production, reserve, and contingent resources. These are three classes, you can say, resource classes. So I'll go one by what is development not viable. So these are discovered accumulation, very low potential, and the decision limited production potential. A decision get what is decision we have taken not to undertake further data acquisition studies on the project. So maybe low potential, volume is less, and right now management taken decision not to go ahead with this project. Next is development unclarified. What is unclarified? Discovered accumulation which is under evaluation, still under evaluation, that commerciality is not yet established. So project decision get is requires active appraisal, further appraisal or evaluation. Should have a plan for future evaluation. Without a plan, this should not be called, it should not figure here unclarified, they should be development not viable. So because now we feel some more data is required, technical evaluation is required, maybe data acquisition, maybe evaluation, maybe interpretation. So then it is unclarified. What is
Mr. 5 more minutes.
Okay, it's a long okay, development on the whole. This project is potential for commercial development, and right now it is a hold because of external contingencies. This temporary contingency may be all these contingencies I talked about, maybe any of the country extra which is beyond control of the operator. Then development pending. This is, you can say, the highest order. This project is established commercial, but decision to move the project to level of technical commercial maturity. Then I got justified and approved for development. Decision is to go ahead with the development, financial commitment. Next will go approved for development. Field production and is generating revenue. So reserve category, similarly, reserve can be proved probably possible. I think everybody knows that. I will not go into the 10. And they can be say 1P, 2P, 3P, already I explained. And there 1P is equivalent to P90, 2P is P50 and P10. So P90 is at least 90% probability that the remaining quantity actually recovered will equal exceed the proved reserve. When it comes to PD plus PV, that is 2P, at least 50%. That is the 50% probability that the actual remaining quantities will be recovered. So again, the reserve can also, by economic status also, it can be developed, it can be undeveloped. Now ONGC has migrated because we had the job, because we are almost 380 fields, so we have to migrate to PRMS. It was a big challenge. In 1 year, we have to do it. I already talked about this. How we achieved this? So existing reserves on SP system, and when it was a challenge when we migrated to PRMS, we have contingent resources. We have to identify field not put on production, not producing field, no farm plan, never produce pay horizon the producing field, non-producing horizon producible, underperforming field. They constitute actually, we identify they should be put in contingent resources. Reserves field on production, producing page, and we have considered the profiles. Based on that, reserves are split into contingent resources. Bulk of the reserve in PRMS, or maybe probable and possible, they constitute bulk of the contingent resource in PRMS system for us. So it looked like this. When SP system, we had discard PIP, recoverable, production, and reserve. There is no contingent resources. Calling it UR. UR must refer the associate technical commercial condition. It is basically recovery. Earlier used to be called ultimate reserve. For us, UR we have taken production plus reserve plus contingent resources. And PRMS says you should always refer associate technical and commercial condition. Our table always refer below the table. UR is production, reserve, and contingent resources. So I'll say how some of the fields. When it was SP system, we had everything in reserve, ultimate reserve, and reserve. When you convert to PRMS, it is a discount field which is not monetized. Of course, when it is not monetized, there will be no reserve. So as on today, after converting, there is no reserve. Every went to the contingent resources. Another field is discovered in recent past. That is after PRMS application. When after PRMS have not is monetized, development plan is not made. So it's assumed that all the recoverables will be contingent resources. So there is no reserve. UR is equal to contingent resources. Producing field on the additional page of development. That is it's a field, old field when I think it has passed so many development pages. It has undergone number of development pages. And presently we have earlier system where 3P reserves were there. Now we have split into reserve and contingent resource. This contingent resource belong to a layer which is yet to be exploited. There is no development band currently not producing. It's a brown field. So there is no contingent resources. And there is no layer left out here which is unexploited. So everything, it is as per our profile, production profile, we are going to be produce this result. What ONGC we have done for implementation sensitize of PRMS, what we are doing today workshop, we have conducted workshop. We have 10, 13 assets and 6, all the basins representative. We are given a workshop conducted, not only theoretical, we have our own guidelines to follow. Though PRMS guidelines are for company specific, we have capture because we are capturing 380 fields and it constitutes maybe 1500 producing layers. It's a Herculean task. So we have developed, maybe first year we had some glitches. Maybe second year, after second year, now we are more or less regularized and streamlined. For that, this work, our group was this in the end, Dehradun, the PRMS team was awarded also. Our corporate also recognized their contribution. So how we do third-party certification? Over the years, we have been doing it. And last year, we have done 2019-20 also 160 clusters, which is almost 201 fields. And our PDD reserves were almost in sync with what we are having after PRMS. They're matching. They've been vetted by the third party and they're quite matching with our PDD reserves. So this is the point of discuss deliberation. I think DGH has issued a guideline at 10th March that it should be schematically represented from 1st March. So for us, entities with a single field or 2 fields or 3 fields, they can make a schematic representation. PRMS does not say you represent it schematically. Pictorial depiction of hundreds of fields and thousands of pages is a difficult proportion, will not add value to the reserve reporting. ONGC capture resource classes and reserve categories and they are best depicted in tabular format reflecting essence of PRMS. But I feel reserve statement is akin to a financial statement of company and it is best represented in a tabular format rather than a schematic pattern or pictorial format. So this is our point for ONGC side. I think DGS to consider this thing. So typical ONGC, how the table looks like. When you tell in place volume, that discount PIP. When you tell UR, that is recoverable. Commercial, part 2 parts, what is production and reserve. When it's of commercial contingent. All the essence of contingent resources are captured here. So there is no need of pictorial format and making, can you imagine 300 fields and 1500 layers in pictorial format, how the software will be captured? ONGC scale, we can make a pictorial representation. Okay, thank you. Thank you for hearing me. I have taken 2-3 minutes extra.
No issues. Thank you. Thank you, Mr. Das, for giving us insight into the PRMS philosophy and how ONGC has adopted it. And now I would like to invite Mr. Harshvardhan and Mr. Shashank Singh from Cairn Oil and Gas to present their paper on Ravva Field, Technology Implementation to Realize True Field Potential and Wave. So over to you, Harsh and Shashank.
Thank you, sir. So I'll be presenting my screen. So is my presentation visible?
Yeah, it is visible.
Okay, sir. Yeah, so good afternoon, everyone. I hope I'm audible as well, right? So at the onset, I would like to thank DGH and Cairn Vedanta for providing the platform to present our talk. on Ravva Field. So, as most of the eminent panelists and speakers have already talked about the framework of PRMS guidelines. So, our talk basically essentially is more towards kind of case study where how we have applied technology to consistently increase the reserve base and production so as to increase the field life and optimal decline management. So essentially, we'll be going by like 4 ways how we have done that, like systematically how we have applied technology at every stages, then how we have converted the resources to reserves using proper characterization of uncertainties, and then taking it to development and for field development, and also following PRMS guidelines extensively, like what we have adopted in Cairn before also from 2007 to 2018, we have been following the guidelines. So essentially this will be the outline of the talk. So first, I'll be taking you through Ravva block overview. So Ravva block lies in the eastern coast of India in KG Basin. So we have 8 platforms here, and they are located in water depths of 10 to 15 meters. And onshore plant capacity is around 90,000 stock tank barrels. And currently the production what we are having is around 18,000 BOEPD. That includes around close to 300 million barrels of oil and 374 BSCF of gas. And EUR till 2029 is around 320 million barrels. So this is how we stand in the block. And our participating interest is 22.5%. One is pre-production sharing contract. So it stands from 1978 to 1994. So there, what we did, we had 2D acquired, then we drilled few wells, couple of exploration wells, then we had success. Then first technological implementation was using streamer survey. So that was done here, and then we drilled 21 wells from 1990 to 1993. Then platform was installed and commissioned, and then first production was done in 1993. And then PSC was signed in 1994. So that was the outline pre-PSC. Then post-production sharing contract, what happened was we drilled most of the wells until now it's more than 90 wells in the field. So it was like, if you broadly, if I characterize what kind of technologies we used after that, was like 2001 we had OBC 3D data, which was a game changer in context of Ravva. Then using lots of attribute works like fluid factor volumes and AVO characterization was the cornerstone for all the development activities. And it was integrated with a well-rounded effort from both reservoir engineers and petrophysicists and geologists, and these campaigns followed. Then we had in 2009-10 we had OBC acquisition and processing, 4D OBC. So 4D data was acquired here. Then we had successful drilling campaigns post 4D data acquisition in 2011. And also we did some studies based on 4D interpretation because it gave a very good quality high density data. And we did some successive campaigns in 2014-15. Currently in 2019-20, the latest one, we drilled 7 wells, and this was mostly towards the small pools. I'll be talking briefly on this also, how technological implementation helped realize the potential of this and how we converted into reserves category. So this is how it is. I would like my colleague Shashank to take a couple of slides here. Shashank, over to you. If we look here in the Ravva Field, the plateau period was extended for a larger part from 1997 to around close to 2007-8, and then we had decline. So how we use technology to arrest the decline and add reserves, so I'll be talking here. So as I mentioned before, in 2001 and 2 campaign, we started drilling after OBC 2000 data was there. And in 2006 to 8, in the phase 3 campaign, what happened was we in phase 4 and 5 was mostly application of high density data and HD data, which we acquired, we called 4D data. And then in phase 6, what happened was good uncertainty estimation and then try to develop these pools. So we did that kind of work here. and that was a very good development campaign. We were able to double the production. So that is how it stands.
Shashank is back, Harsh, if you...
Okay, Shashank, you want to take the slide?
Yeah, sure. Thank you, Harsh. So basically, this slide summarizes on how the wells were drilled in each infill campaign have contributed to the overall field production, and emphasizes on how the technology has been at the forefront of every drilling campaign and how it has helped us in achieving the recoveries from the field of the order of almost 50%. The details regarding the contribution of the 4D seismic and the AVO field factor and spectral decomposition in the drilling campaigns will be covered by Harshvardhan in the subsequent slides. Can you move on to the next slide, please?
Yeah.
Yeah. So this slide basically, before I talk about the reserves progression in Ravva over the last 25 years, I want to highlight that the reserves and resource reporting here at Cairn is strictly based on the PRMS guidelines. So we have a robust internal functional assurance process that guides us during the reserves reporting exercise, and hence helps us to adhere to PRMS guidelines. In addition to that, every year we have a third-party independent estimate. And that, as we drilled more and more wells, the amount of data available to us increased. The integration of this reservoir and the production data that we got from these wells has helped us to gradually increase our EUR and also upgrade reserves from possible category to the proved and probable category. So right now, the current estimate, 2P EUR estimate stands at around 382 million barrels of oil equivalent. Next slide. I think over to you, Harsh.
Yeah, thanks, Shashank. As I mentioned before, briefly now we touched upon how the reserves progression has gone about in Ravva Field. Now the key technology enablers that has helped in realizing this, I'll be discussing in subsequent slides. So first one is the AVO technology, which I mentioned before, the use of fluid factor attributes. So essentially in Ravva Field, because of the rocks are giving us a response for the fluids, so we are able to characterize hydrocarbon bearing reservoir in increasing the resource base and subsequently the reserves. So and also we have used this technology in identifying bypassed oil using integrating the 4D data. So I'll taking with that as well. So essentially by the use of 4D data, we were able to characterize how the waterfront has moved in the reservoir and where are the bypassed oil. Like you can see in the line BV dash, you can see these are some of the bypassed oils which have been left and were optimally planned in the successful development campaigns. And also you can see in the seismic, like the effect of water flooding. So if you just look into the base survey versus the monitor survey, you can see that water flooding is giving us a good indication in the amplitude response. So, so this was the cornerstone of using technology in guiding the resource and reserve base. And also the fault seal characterizations were also understood based on these, because there were some small faults also sealing in Ravva Field. So that gave us good insights about the fault seal characters of the field. So 4D data has helped us tremendously in that respect. And yes, I'll just quickly summarize it. So for LLM sand, as I mentioned before, which we did in the current development drilling campaign, we tried to identify some of the very laterally restricted small sands. So first, like sand fairway identification using spectral amplitudes, then characterizing fluid factor maps for these, and then a detailed fluid factor characterization giving us understanding of the connectivity, because we are going to place a producer injector well at optimal locations. So this had to be very appropriately. Next, I'll be taking you the way forward, what we have in store in Ravva Field. So using the help of technology, we are extensively characterizing the prospective resource, both in terms of characterizing the uncertainty in a best possible manner, adhering to shallower late Miocene as well as early Miocene prospects. And we have close to around 160 million barrels of prospective resources kind of matured. So that is where we stand right now. So that is all from our side, sir. So this is all I'd like to conclude. Thank you.
Okay. Thank you. Thank you, Shashank, for finishing it before the time. And thanks for giving us a good insight into how technology has helped in not only maintaining production from Ravva and also. So I wish the story continues and you have more success in future. So thanks again. With that, now I invite Mr. Dustin Fife from RIL to give his talk on hydrocarbon reserves and resource estimation in deepwater fields. So welcome.
Thank you, Amitabh. Let me go ahead and put my presentation up. Can everybody see me? No? Can you hear me?
Yeah, we can hear you.
You can hear me?
We can hear you, Dustin. Yeah, we can hear you.
Okay, let me try my camera again. Oh, can't see me. Oh, well, that's probably better. You can see me on the screen. Okay, let me quickly put my presentation up. Okay, welcome everybody. Thank you for the great opportunity to present today. It's always an honor to be able to present in front of a prominent group like this. So thank you very much for the opportunity. I thank Reliance for giving me this chance to present today. So I'd like to just talk about the PRMS use in deepwater fields on reserves and resource estimation, the progression from all the way from our resource perspective estimates in through production and reserves. So let me make sure I know how to use this. Here we go. Okay, a little bit of background on PRMS. Many people have done a very nice job today describing the use of PRMS the way it's designed right now. I mean, I really thought that Barnali had an excellent point, and in my view, the most useful point that the update of PRMS had, from my view, was the clarification between P1 and 1P. I think that has, in the last 10 years since 2007, always been a little bit of a loose part of PRMS, and that is much better explained now. So PRMS is a system that was put together to try to harmonize the method that we in the oil industry estimate our resources and progress this through into reserves. And I was glad to see there were a number of people in this meeting today that are from my generation of the industry, of years of experience in the industry. So people may well remember that PRMS really was an offshoot of the increased corporate governance from the mid-2000s, from the Sarbanes-Oxley movement, where there was a much stricter rule on companies to stand behind the estimates of value within their company. And so the SPE and the World Petroleum Congress and a number of other very prominent groups got together and agreed for PRMS, and it was introduced. And so as a result, I mean, I've seen, having myself worked in many areas for a few very large companies, have been really pleased and proud to see that PRMS has been adopted, widely across the world right now. I mean, I just saw a presentation from ONGC's adoption of PRMS, and it's very, very nice to see, very glad to see that it is so well adopted here, because it gives us a common language to talk about our progression of resources to reserves, something that's recognized now across the whole industry, which is highly valuable. Because the nature of our business in oil and gas is risk, uncertainty and risk. And so because of this framework, we are now able to talk about how we convert this uncertainty and risk into a project that is potentially commercial. And we in this industry don't deal with projects that are small. These are enormously expensive and valuable projects. And so managing this risk and uncertainty is absolutely critical. What's also interesting in the last 10 years, or I would say probably a little bit longer than that now, 14 years, but since the original PRMS was introduced, was the technologies that have evolved within the oil and gas business. and the different types of fields that have come to be prominent and economic in the oil and gas business. And move to the next slide. Some of these developments, were not really imagined, as recently as 10, 15 years ago. The shale gas, shale oil, deep water was still relatively new. So those are just a couple of examples that the original PRMS probably didn't try to address directly. But now, since these developments have become such a critical part of our industry, they required an update to account for some of these risks and uncertainties and how to properly manage those. In preparing for this presentation, I was doing a quick search on the deepwater developments in the world, and there was a recent estimate that up to 40% of the existing resources for development are deep water right now. So it shows that there's a huge value in clarifying the way all these deep water projects are properly matured. So just to give it a couple examples, in deep water, one of the things that we deal with is cost. I mean, in conventional oil and gas, obviously, me coming from the US, onshore US, you have that ability to delineate fields quite easily, to manage your cost a little bit better. However, in deep water, you're constantly trying to, after you discover the field, to delineate and appraise at a minimum cost, because you don't really have the flexibility for multiple well tests, additional delineation wells, when your wells could cost upwards of $250 million. It's just an economic limitation in doing our delineation deep water. So PRMS has responded by allowing greater use of seismic interpretation, greater use of seismic data to allocate resources within these fields and progress that resource progression forward without the use of some of the more typical tools. However, in using some of these resources like seismic, we have the basic nature of a seismic resolution, that we don't have a lot of the resolution necessary to give extremely clear ideas of things such as petroleum volumes, contacts, various elements that are important for our resource assessments. And so PRMS 2018 did update a number of these elements that can be used in this assessment process. So I'm going to just quickly go now to an example of how within RIL we are applying these principles in the maturity of a deep water field. I'm just showing this coming out of PRMS again. This is a very familiar slide that's been shown a few times before. Following the prospective resource work where you have the undiscovered petroleum in place, which is usually based on a very wide 3D seismic or a basin modeling project to assure that there is the potential of hydrocarbons in the area, that there's enough of a generation system to generate the hydrocarbons, and that there are potentially trapping mechanisms. This is a hydrodynamic conventional system, obviously. And so once that is assured, then companies will take that chance to drill exploration wells. And once the discovery is made, we go into the appraisal mode. The appraisal mode is where we gather that data, and in deep water, it is gathered pretty much up front in the whole project. You try to, like as I said, you try to minimize your expense because it is so great, and all that expense goes into the capital allocation pool for any development economics. So you have to always be careful on balancing the amount of data, the type of data you take, and that cost toward that future development. So once the appraisal is done, it goes for commerciality and then follows for FDP approval and project estimation. And so purpose of this meeting, I'm just going to use the D34 area, which has recently come on production. And so in any of these projects, especially in an area that is somewhat mature, like the KGD6 basin, we have existing projects that have gone through the production phase. And so we have some analogs and some examples that we can use. And so that is very important in all the delineation and understanding of these fields. So after exploration has discovered the field, we go into the appraisal. In the D34 area, that included, as can be seen in the table on the right, under the appraisal DOC column, it ultimately included 3 plus 2 appraisal wells for a total of 5 wells. At that point, it estimated about 5 producible reservoirs. The data taken was MDT and core. Oop, did that go off?
Sorry, we lost your presentation. You may have to
Yeah,
reshare.
it closed itself. I mean, this is working from home. I think we're all used to some of these little unexpected
Yes,
problems as we go, and we've learned to roll with it. So, okay, so back to this. So we gathered a certain amount of data, and at that point, it was felt necessary, or felt it was adequate to go into the full evaluation process. And so from that data acquisition phase, we move to the next reservoir characterization phase. And as I said, in a deep water setting, we depend very heavily on seismic. And you can see that reflected in the seismic industry. The methods of interpretation, some of the inversion methods, geostatistics, have matured, have come a very, very long way within the last, I would say, 15 to 20 years in my experience. And so the amount of tools we have right now has come orders of magnitude in improvement. And so we, after taking the data, we apply that seismic interpretation to the well data we've taken with the seismic ties, interpretation, the log data, integration, everything. And this creates pretty much our basis for a static model that moves next into the geocellular modeling. From that, we integrate the well log, the core data, all the image log data, we process the logs, and we feed that into the property model. At the same time, as I said, heavy emphasis goes into the seismic for its inputs into the facies modeling and also into some of the structural modeling, obviously. A side note there is additional seismic attribution analysis can be used where necessary, where we feel it's mature enough, and that is added in the data calibration. From this, facies models, porosity models, and saturation models are generated, and that goes into our volumetric estimation. So all this is done pretty much up front before the FDP, using the seismic data to heavily influence the field development plan or the geocellular model that is used for the field development plan. Moving from that point, we go into the development plan, where we take that geocellular model that has been developed from all the data available at that point, and we go through a series of realizations, trying to judge what is the best plan for the field and how it can be done with the minimum number of wells possible. Because again, this is a very cost-sensitive type of development, and so that's why a considerable amount of time and effort is put into judging what the proper well design, what the proper number of wells, and what the proper risks that need to be incorporated into this are made at the FDP phase. So this is where analogs come in very closely. And we've learned over time through our own experience and other field operators' experience that one of the greatest risks we have here, and I would also say this is a common risk in other areas, other turbidites, is water movement, unexpected water movement. And so we use that experience in the development of this field development plan, where we know that the wells have to be designed in a way to where that standoff is maximized from any potential aquifer. We also learned that there needed to be considerable insight into what that water production risk is, and has influenced a number of our production plan decisions, and also in lesser extent at this phase in the development into the later well designs and how they were placed to manage that standoff risk. So all of this comes together into the field development plan. But if I may go back one slide, 2 slides, you also notice the FDP included a well count of 6 + 3, but then for final development, we have a final well count of 6, because as we went through, we saw that we were able to develop the number of reservoirs that we considered commercial at that point within 6 wells targeting 4 reservoirs. And so the FDP may have additional opportunities, but that has to be matured with information gathered by production. So this is what I would say is where we put a considerable amount of our effort, and that is in analyzing the field performance based on production coming in. And this is something that in Reliance we have as an evergreen process. It is constant. We use our, just move that here. We use reservoir models on a production basis. We are continually monitoring our field performance from downhole telemetry, our pressure temperature gauges, our flow measurement. Everything is incorporated on almost a daily basis into the reservoir performance. Now this feeds back into that whole process of evaluating deep water. We don't have the luxury of easily running surveillance logs or easily running any type of remedial work if we ever saw the need. So we have to depend on some fairly basic tools, pressure, temperature, and rate, on some very complex decisions. And so that is why we use significant emphasis on our geocellular modeling, our reservoir simulation, the amount of simulation realizations we run to try to capture every realization that we might see in terms of the well performance. And so it's very heavily based on a constant, non-stop surveillance of the fields. So where are we right now? This is where, just to show quickly, the initial development we were able to achieve with 6 wells. As you can see, that although it is 6 wells, we are targeting 12 penetrations in the mid-Miocene, 3 penetrations in the late Mio R1 upper, and 2 penetrations in the late Mio in the AV1 upper. And so we're able to optimize based on our capital expenses the number of wells targeting the number of reservoirs that allow us to drain everything that is within the connected volumes at this point in time. And so as we produce the field and as we assess the connectivity throughout our constant surveillance, we will judge if that is the appropriate well number for draining this field, or if there are other opportunities of bypass gas or areas of non-connected gas in the future, and we will address those at that proper time. So where does that leave us now? Size the FDP model correctly. So we are now moving away to what, based on some of the depositional models and depositional scenarios that we see now, how would some of these other depositional analyses alter the long-term view on the architecture and the geomorphology of the field? Is it something that we will see additional opportunities, or is it something that some of the alternate models will help us understand additional potential that we see in the field that may have been missed with the limited data set we had going into the FDP? So this again is just trying to use as much data as we can in moving forward and capturing all opportunities we might see in front of us. Geostatistical inversion has proven to be a very promising tool. So it is being used more. It's still in the evaluation phase, but we have some very high optimism for its improvement in characterization of our fields. The ultimate recovery, as I said, is a constant and ongoing process that we use production on a daily basis using simulation in a very aggressive way. More in a production phase than you would probably see in any other, say, onshore or shallow water offshore development. We are currently now looking at the use of top-down reservoir modeling to increase the number of probabilities and move into a proper probabilistic estimation instead of deterministic, so that we can capture all the uncertainties and we can align our low, best, and high cases with our P10, P50, and P90 ranges of uncertainties. And then also the last thing is deep water, just to mention as a sort of the last point, deep water is highly sensitive for its flow assurance on the surface network or the subsea network. And so we have very, very rigid rate restrictions that the wells and the flow lines have to operate at. And so that adds another component of risk that needs to be managed for the long term. And so as I was mentioning, the subsurface reservoir modeling is done at a very, very rigorous and robust method on a daily basis almost. That also includes the surface modeling, where we have a very good integrated asset model to help us understand if we have flow instability predictions, if we are having, water problems that are causing in the incline phases of our subsea system some potential surging or slugging. And all these things we have been able to model effectively and prevent, and gives us much more confidence in terms of our long-term sustainability for this field and to achieve our ultimate goal. And just to remind people that one of the heavy elements of PRMS is to use the evidence that the existing gathering system is adequate to produce the levels that you are predicting within your reserve estimations. And so we integrate that very closely into all phases of our predictions for our deep water fields. And so how am I doing in time? Am I over?
Yeah, so Mr. Dustin, sorry to interrupt. So we are running a little over time. So
of course.
My mistake, I did not buzz you at 10 minutes, but I hope you are covered.
I'm done. So that's
thank you so much.
Okay. So am I open for questions, or Amitabh,
We will have questions towards the end of the session. So
okay.
Not immediately, but thank you for your assessment of the improvements in PRMS and your case history on the D34, focusing on the deep water development. So that was very, very interesting.
Thank you.
And now we'll move on to our next presentation. It will be by Mr. Pankaj Kumar from Antelopus Energy. And he will be talking about evaluation, classification, reporting, and auditing of D12 field. So over to you, Pankaj.
Thank you, Amitabh, and a warm welcome to all our distinguished guests for attending this workshop. So I'll just share my presentation. Just give me a minute. Okay, Prasanjit, I think there is some issue with sharing. Can you please put up my slides?
Yeah, I'll share from my end.
Yeah, thank you so much. Thanks, Prasanjit. A very good afternoon to everyone. Basically, this presentation is regarding the workflow that we followed for reporting of results in one of our fields, the D12 field. So I'll take you through what were the workflows we followed during the all the processes of the subsurface work, the facility work, and finally on testing the commerciality of the recoverable volumes, finally culminating into booking of reserves for this field. So as a background, the D12 field is located in the D31 cluster in the prolific Mumbai basin in the western coast of India. So this field was awarded to us in the second round of DSF. And since then, in the past 1.5 years, we have progressed to carry out all the subsurface work and finally submit the FDP, have the FDP approved, and maturation of the recoverable volumes from this field into the reserves category. So location-wise, the field is located in the Mumbai basin, as I said already, with a water depth of approximately 90 meters. The total block area is around 250 square kilometer, with total 5 discoveries in this block, D12 being a gas discovery, and other discoveries are D31, B192A, BH61, and BH70. So for the D12 well, in terms of data availability, there was one discovery well drilled in it in the early 80s, and in the top Ratnagiri reservoir, we had there was a test of 4.8 million standard cubic feet of gas with an associated condensate rate of around 440 barrels. And subsequently, after carrying out all the subsurface work, we submitted the field development plan, and reserves were estimated for this field. In terms of data availability, we had the 3D seismic data, and another vintage data was also available in the NDR, which we subsequently purchased and included it in our analysis. And regular well logs, the DST data, formation evaluation report, and reservoir studies report were also present for this field. Next slide, please. Okay, so we followed a standard workflow. So here in this slide, I'll just give an overview, and in the subsequent slides, take you in detail through each of the steps for the subsurface workflow. So first is the data integration. One thing to note here is that the data availability was quite scarce. A lot of data we have to also take from nearby wells, nearby fields. A lot of analog data had to be analyzed, and a good regional understanding had to be built up. So data integration from all available sources was very important for starting the subsurface work for this field. And then the regular workflows of seismic interpretation, wherein the time of the well, the horizon fault interpretation, conversion of the time map to the depth maps, and mapping of all the horizons and faults were carried out. That followed with the petrophysical interpretation, of which involved conditioning of the logs, interpretation, assessment of the petrophysical parameters and the related reservoir properties. And finally, the geocellular modeling for coming up with the static model, which included the integration of the structural model, the petrophysical models, to finally come up with volumetrics of this field. And that would then tie into the reservoir engineering analysis and the forecast for this field. Next slide, please. So just as an introduction on the stratigraphy, as I said, this field is located in the Mumbai offshore. It's a tertiary basin with a mixed carbonate and clastic depositional system. The Ratnagiri field, what we are talking about, is of the Miocene age, and there are several analog producing fields in the basin. So that gave us a lot of data for developing a good regional understanding, and the analog study also helped us in defining a robust development strategy for this field. Next slide. So as I said, the first phase of work was to integrate all the data available from this reservoir and also from the nearby wells which were present inside the block, to come up with a regional well correlation. As you can see here, for different fields, right from D12 to BH61, we created a well log correlation to understand the overall reservoir correlations spanning across the block area. And also we had included. So the next step was to come up with the seismic interpretation. So as I said, we had seismic data available to us with the docket, and also some additional vintage seismic data was purchased. Seismic to well tie, so that we have more confidence on which velocity model we were using to convert the time surfaces to depth surfaces. And also some seismic attribute analysis was also done to give us more confidence about the hydrocarbon accumulation. As you can see clearly on the seismic window, we can see dimming of attributes, the RMS amplitudes at the top of the structure. And basically this dimming conformed very well to the interpreted gas water contact what we have got from the log and the DST information from this well. So that gave us a lot of confidence on the contacts that we were taking, and also a confidence on the RMS amplitude interpretation, which basically also conforms very well to the contours in this area. And we can clearly see that basically it forms an anticlinal structure with faults being bounded by faults on the eastern side and on the southern side of the field. Next slide. So basically this seismic interpretation, then it was used to construct two-way time maps for at the Ratnagiri level. And then after integration of all the available data and tying the well to the seismic, we came up with the depth maps. And as I already said, it was an anticlinal structure with you can clearly see two culminations there, the major southern culmination and the relatively smaller northern culmination, both having an anticlinal structure bounded by fault on the eastern and the southern side. So that was basically the structural work that was done for the Deepwater field. Next slide. Okay, so next is on the petrophysical interpretation. So you can see the the log data that was available to us. So that was used to create the Pickett plots in order to estimate the saturation parameters. So the Indonesian method was used to calculate gas saturation corner, wherein we see the V shale being calculated, the saturations being calculated, and the pay flags being calculated. Next slide. So once the petrophysical interpretation was done, we followed the standard geocellular modeling approach, which included the steps like the setting up of the structural framework, wherein the geometry of the reservoir, the interpretation of the faults, mapping of the faults was included, and that after that we went for the reservoir correlation and zonation of the reservoir, where a layering scheme was created in order to capture the heterogeneities available in the vertical sensors related to the suitability of using this same grid design as we go into the dynamic simulation model as well. After the grid design was finalized, the next step was on the facies modeling side, wherein the
Pankaj,
little
5 more
facies
minutes.
were okay, okay, sir. And on the facies modeling, and then the petrophysical modeling was also incorporated to finally come with the geocellular model, which was then fed into the dynamic simulator. Next slide. So again, this just gives a snapshot of the same geocellular modeling workflow that was carried out for the D12 field, wherein we set up the structural framework. The logs were upscaled, the facies modeling was done, then the porosity modeling was done using the SGS method, then combined with the saturation modeling part, it led to a final volumetrics, wherein we estimated the gas volumes that are present in the reservoir. Next slide. So then the other important piece of data available to us was the testing information. As you can see, 3 zones were tested in this reservoir. The first zone was the bottom one, which produced a combination of gas and water. And the top 2 zones marked by arrows with the second and the third box, it produced clean gas. So this basically helped us identify the top of the transition zone and the gas water contact for estimation of our final volumes. Next slide. And then integration of all that led to estimation of the in-place volumes for the 1P estimate, wherein we considered just the southern culmination, and for the until the top of transition zone. For the 2P estimate, we considered both the culminations till top of transition zone. And for the 3P estimate, we considered till the gas water contact for estimation of volumes. Next. So once the geocellular model was ready for dynamic simulation, we incorporated the available PVT and SCAL data, and then initialized the model, checked the model for standard QC processes like for model equilibrium and estimation of gas in places. Since DST was a very important data available to us, we used to calibrate the dynamic model with matching the DST results in terms of the produced rates and the available flowing bottom hole pressures. Once we had sufficient confidence on the dynamic model, we created different sensitivities for all the cases, taking into account different parameters. And finally, on our best confidence case, we came up with the field production profile, basically, which is the technically recoverable resources for the 1P, 2P, and the 3P cases. Next case, next. So this in overall summarizes, like from the geocellular model using different parameters of GRB, net to gross, saturation, porosity, BG and CGR. For the low, mid and high case, we use the volumetric parameters and then finally come up with the in-place volumes. And then with the dynamic, using the dynamic simulation, we created the production forecast for all the low, mid and high cases. Next slide. So the next important thing for booking of reserves was testing on the commerciality and the development scheme. So we had a robust development scheme for bringing the D12 field on production. As we know, it is located in the Mumbai offshore basin where a lot of infrastructure is already existing. So using the existing infrastructures, evacuation of gas was not a problem. And also on the western coast, it is a readily available market to us, and the talks are already in advanced stages to tap that market. So in terms of meeting the commercial criteria for having a robust development scheme and available market also, this field satisfies that for being moved to the reserves category. Next slide. So once the development scheme was finalized and the capex estimates were available, so basically that in combination with the OPEX estimate, the production profile, and using the production profile, a cash flow scenario was built for this reservoir, and wherein we also carried out uncertainties on the major parameters. Based on that, we were able to estimate an economic cutoff for the TRR, and then based on that economic cutoff, the estimation of reserves was carried out for this D12 field. Next. So as again to summarize on the PRMS guideline, as we can see that the D12 field satisfies all the criteria to be booked under the reserves category. As you can see from the definition, there is a discovered resources. The recoverable volumes have been estimated using robust subsurface workflows. The development concept has been finalized. The commerciality of the project has been established. And in fact, we have already started some capex investment into the project by carrying out works like the geotechnical and geophysical survey on the field. So as per our estimates, the D12 field sits into the reserves category, into the subcategory which has been approved for development subclass. Next slide. So after estimating the reserves internally, it was important for us to get these reserves audited by an international auditor of high repute. So we engaged with an international auditor, and they also came up with independent estimates of the reserves from the D12 field and also from other fields that Antelopus has as a company. So based on their assessment, they validated the workflow that we had followed, and also the numbers, independent estimates that they came up with conforms very closely to our estimates. The variation is within 5 to 8% of the numbers that we had estimated on the company-wise and individual field-wise level. So all in all, to summarize, it was a good confidence booster for us that having our reserves audited after following robust workflows, all of them conforming to the PRMS guidelines to come up with the reserves estimate, has all translated well into the booking of reserves for the D12 field for us. So that is all from my side. Thank you so much, and thank you to DJH once again for organizing this workshop and giving me an opportunity.
Thank you.
Thanks.
Thank you, Pankaj, for your very, very good presentation on the D12 field development planning. I'm sure it's not easy when data is relatively scarce, and good luck with all your development. So before we move to question and answer session, I think we have Mr. Shakir Ahmad Chaudhary, whose presentation got accepted in the second session. And since that's a very, very important and interesting presentation, we would like to complete it. So it will just take 5-6 minutes, I think. So Shakir, if your connection is good, you can start and complete it.
Yes, sir. Okay, so thank you very much, sir, for allowing me to continue my presentation, as I got interrupted at the middle of my presentation due to network issues. In the first half of my presentation, I touched upon how Oil India has adopted PRMS 2007 very timely, and we have also updated our reserve books following the latest guidelines. And thereafter, I dealt a little bit on the PRMS basics, Thereafter, I showed how Oil India has aligned its activities in exploration, appraisal, and development phases to estimate our reserves. So now I'll be continuing with my presentation, where I will discuss how Oil India, following the PRMS, calculates its reserves. So as you can see, we are estimating the reserves under the three categories of 1P, 2P, and 3P. And our subdivision of reserve categories is made into developed and undeveloped components based on the activity required to produce the recoverable volumes. So we calculate the proved developed producing component based on the recoverable volume from the existing producers. Thereafter, we calculate the proved developed non-producing reserves from the potential that is forecasted from workover operations. And then we also book the reserves under the proved undeveloped category for those potential that will be recoverable from the future wells or from activities which involve investments comparable to a drilling cost. The reserves under all these three categories of PDP, PDNP, and PUD statuses are finally added to get the total reserves of a reservoir. Next, please. So developed reserves estimation methodology. Here we estimate the PDP component of our developed reserves by employing exponential decline rates till the end of the PML validity to estimate the 1P reserves. And an optimistic decline is considered by extrapolating the production trends up to the economic limit of a reservoir for calculating the 2P and the 3P reserves. Next, please. This is how we book our PUD reserves. I'll be showing this with a case study. In the PUD reserves are booked when the field development plans with future drilling locations are planned for maximizing recovery from a project. So here, as you can see, I'm showing how the PUD reserves have been booked in one of our fields in Assam. The first exploratory well 1 was drilled in an identified prospect in 2017. The well was a commercial discovery where we had encountered a reservoir thickness of 35 meters. The reservoir extension was then delineated by drilling an appraisal well 5 in the southwestern part of the structure. So the probable and possible reserves have been upgraded to proved category based on the appraisal well drilling, well 5. And PUD reserves, by following the PRMS guidelines, we usually consider one outstep location for booking the 1P PUD, and we consider two outstep locations to book our 2P and 3P PUD reserves. So with the successful addition of the results from the appraisal well drilling, we have managed to upgrade our 2P and 3P reserves to proved reserves, and we will bring a greater chunk of these proved reserves into production by placing suitable number of development locations in the structure. Next, please. Reserves booking for improved recovery projects. This is another important aspect while booking of reserves as per the PRMS 2018 guidelines. So PRMS guidelines, they provide scope for booking reserves for the additional recoverable volume beyond the primary recovery of a reservoir for any ongoing or planned secondary and tertiary recovery methods. So we book 3P reserves when there is an existence of a favorable indication from deployment of improved recovery methods in a reservoir based on laboratory results or simulation studies. And we book 2P reserves when there is a commitment to implement a candidate-specific improved recovery method, or there is an existence of a project that is approved for implementation. And we book 1P reserves only when there exists a favorable response from an ongoing pilot in the reservoir, or there is an ongoing program in the same reservoir or in an established analogous reservoir. So any incremental recovery from improved recovery projects are booked likewise. Now coming to gas reserves estimation methodology. In oil, we have recoverable gas resources and the gas reserves. So these are
Mr.
two
Shetty,
components.
sorry to interrupt, but could you try to wrap up in next 2-3 minutes? Is it possible?
Yes, sure, sir. I'm just at the very end.
Okay. It seems I interrupted at the wrong time.
Seems to have lost. I think we can proceed with the Q&A. If,
Yeah, let's proceed with the Q&A. We are already late. I'll the first question is from Mr. Arunava Mandal from HOEC. And
Did we consider some of the steps for dewatering gas wells? You mean foam lift, that type of thing? Or I think that we have some fairly not relaxed, but aggressive tolerances on the amount of water that we can produce. But the problem isn't necessarily the ability for the wells to produce water. The problem goes with the amount of water that's allowed in the production system, because as I mentioned, the flow line network is quite complex subsea, and with elevation changes and with multiple fields flowing into a common system, that's where the amount of water tolerance really becomes difficult, is maintaining flow assurance and a proper flow stability system. And so we did consider a number of dewatering techniques, but rather than, and we did take whatever steps we could within those guidelines, but we haven't included things like foam lift into the system, because that would just be too difficult to manage on a subsea system. It's difficult to manage on a surface system. So on a subsea system, it would just be unmanageable.
Okay, thanks. So maybe we'll come back to you, Mr. Dustin. But before that, there is a question, not directed to anyone in particular, but if Mr. Das, you would like to address this. The question is, once water contact is established based on logs and testing results, is it okay to have 1P, 2P, and 3P cases based on contact variation?
Absolutely not. When you contact, but in case of transitional contact, then we can have 1P, 2P also. But if case contact is very clear, then you can have 2P, 3P. You can have only one value.
Okay, if it is reliably established, and that's right.
Yes.
Okay, thanks. One last question to Mr. Dustin again, and this is from Rishikesh Joshi. So the question is that, Dustin, you mentioned PRMS 2018 has allowed greater use of seismic, which has helped deep water projects. So can you explain what has changed in PRMS 2018 in this regard?
Well, I can explain it a little bit differently in terms of how, when Deepwater was first becoming a relevant industry or a potential industry in the mid 1990s, that was one of the biggest issues. Excuse me?
No, please go ahead. It was some background song. You can continue.
Okay. It was early on when Deepwater was first being established. It was a fairly tight tolerance, mainly from the SEC in the US, on how the volumes were delineated, and multiple contact points from delineation wells were somewhat required at that point. But as time went on, the cost was just too great. And so the SEC was petitioned by a number of companies, Shell specifically, I remember, because I was a Shell employee at the time, challenging the ability to delineate a field's in-place volumes based on seismic. And I think that it was just mentioned a minute ago, is there a 1P, 2P, 3P on contacts? And I agree with that. If you've got a contact clearly drilled, then no. But in certain cases, wells would be drilled such that you've got a gas shale contact and not really a gas water contact or an oil shale contact. So contacts haven't really been established by the discovery well, or even by whatever delineation wells were drilled at that point. And so it was petitioned to the SEC to use seismic and then use a range of contacts as a result, because the seismic resolution, in a good day is probably about 50 meters in contact definition. And so that is where the SEC started relaxing that rule in terms of estimating in-place volumes based on seismic. And so I don't have the exact quote from PRMS 2018, but I have seen the application of seismic volumes become much more a key tool in terms of every step of the appraisal and the progression, the resource progression process now through PRMS. But that's sort of the background, what led to that.
Okay.
And I think that it is, I would encourage people to go back into the resource definition part of the PRMS 2018 for more clarity, but that's sort of the history behind where seismic use and its application Deepwater came from.
Okay, thanks. Thanks, Dustin. I think with that, we can end this session and break for lunch. And thankfully, it is not virtual. So hand it over to you, Prasenjit.
Okay, thank you everyone for being part of this, and we'll break for lunch now, and the next session starts at 2:30, and we'll see you all then. Thank you.